Good morning, good afternoon, good evening, everyone. So as Berenice says, I'm going to be talking about SystemReady IR, which is a new program. We announced this back at DevCon in October, but it's, we've got more meat to talk about what this actually is and why it's important for building embedded devices. So I got a bunch of slides here. I'm going to try to go through this fairly quickly to make sure that we've got time for questions and to actually chat a bit, because I mean, that's more fun on these things anyway. But I want to give you some background on why we're doing this. So to start with, I'm going to have to talk about the SystemReady program as a whole so that you can see where this fits in with the other things that we do, all of these being really important to the health of the ARM development ecosystems. And then I'll talk specifically about SystemReady IR, why this is important for embedded compute, for edge, IoT, all of those Linux-based devices that we're all creating. I'll go into the details of what's the key elements within SystemReady IR, and also a little bit of how to actually make use of it within your products before we get into the roundtable. So let's just jump right on into this. So to talk about SystemReady, I actually have to go back further and talk about a program that we did before that called ServerReady. And the idea with ServerReady is back when ARM first started looking at getting into high performance compute and server systems, we realized that this ecosystem does not look like the embedded ecosystem, and standards have to be there. If you don't have the standards, you don't really have a product. And there was many meetings and working with our partners to work out what this is, and a lot of engineering work to get the technology in place. But what it came to is we created the SystemReady program as a certification program for platforms to say that, yes, they conform to the technologies that are required within the server space. And the ServerReady program was really, there's 3 pillars that it was built on. The first one is a document we call the SBSA, or Server-Based System Architecture, which is all about the hardware. So what IP blocks you put into your silicon, how you wire it up, how it's exposed to the operating system. Second one is requirements on the firmware, which was captured by the SBBR document, or server-based boot requirements. And that was the one that said, look, if you're building a server, it needs to be UEFI in terms of the firmware interface. It needs to use ACPI, and it needs to provide SN BIOS, as well as a few other things. And that the OS vendors were the ones who stood up and said, hey, if you don't have these things, we can't support you. And then finally, it was based on testing, where we have an architectural compliance suite that goes and it tests the hardware, tests the firmware interface, and gives a report back on whether or not the platform is meeting the spec. We had a huge amount of success on this, right? That went from a lot of, really a lot of debate, a lot of figuring out what these technologies actually mean, a lot of engineering work to get it up and running. But we're now at the point where ARM servers are a real thing. The standards are real. There are enterprise OSs, both Linux-based distros like RHEL, or there's Windows is there, ESXi from VMware. This is a platform. This is how you define a platform, and we're very, very proud of this program. Having had all that success, though, we've wanted to, how can we actually extend that beyond the servers? Just a quick, okay, I'm actually going to come back to this one because this one is a little bit out of order. There's a couple of quotes here on the slides. You can go look at this later, but Leonard Van Dorn from Microsoft and John Masters from Red Hat both had nice things to say about the ServerReady program. So with all that success and getting those standards in place, we started looking at how can we do the same thing for other parts of the ARM ecosystem. But in particular, compute. So we're talking about A-class or A-profile CPUs. We're talking about rich operating systems, as opposed to, say, the tiny embedded microcontroller things. That's another thing. So we're not talking about that. We're talking about rich compute. But how can we bring the standards in there? As part of that, we stood up our Project Cassini, which is looking at solving these problems. And so Project Cassini is looking at standards, looking at the security of the platforms, and then looking at the software ecosystem that fits on top, with the goal of moving from what embedded devices look like right now, which you can see on the left-hand side of very vertically integrated stacks, to finding places where we can have commonality and we can land common operating systems or common technologies on multiple pieces of hardware, regardless of the SIP and regardless of the hardware platform, right? We're hearing from some parts of the industry that they've got heterogeneous hardware deployments, but they want to be able to deploy the same things into them, even though it still looks very much embedded, right? Out of the part of the Cassini program, we realized, okay, there's a set of standards in that goes along with that. And that's where SystemReady IR fits in. But we knew we had to make changes to what it was that we were doing. And I'll go back to this slide. One more. And so we had the requirements that we did for server. And so a bunch of the stuff that was in there made a whole lot of sense across larger parts of the ARM ecosystem. But there's also things in there that are really more tailored towards the high performance compute or the shrink wrapped operating system. So the first thing we did is we started looking at how do we take that SBBR document and pare it down into a smaller base document that then we can have different recipes for, where the base document's common across the ecosystem, and then the recipes are tailored for different parts of the ecosystem. Now, if you go look at SBBR and then refactored as to BBR, what you'll see is interfaces like PSCI and SMCCC for interacting with secure world firmware is common across all. UEFI has really emerged as the standard interface for talking to firmware and for OS loaders to make use of. ACPI is in there. We'll come back to that later. Exceptions, sometimes we run into exceptions. It deals with that. SMBIOS for describing what the hardware is. And then there's also device tree. Again, I'm going to talk more about ACPI and device tree in a few minutes. So with that as the base, then we've created a number of different levels where SBBR is a recipe. Again, it's back into the ServerReady. But we also have EBBR and we have LBBR. EBBR being, again, another thing that I'm just signposting here because I will talk about it in a few minutes. But it is a community spec that was created within the Linux community on what works there for Linux distros to be able to land on platforms. Right. So we've come up with this set of standards that we took from ServerReady and moved into SystemReady. Again, more on that in a few minutes. So let's move on. To sum up SystemReady, really there's one key vision of this, and that is ultimately we want software that just works. We know from ServerReady what that looks like in the server space. Now we want to work out what does that look like in the larger ARM ecosystem. So what it's built on is, first of all, to have compliance programs at the base of it, so that when platforms want to do the work to be standards compliant, they've got a way to say, hey, we've done this, we've done the due diligence, we've done the work, here's a badge that says that we're compliant. We want the software to work seamlessly across the ecosystem. We're focusing on the common components of the software stack, the hypervisor, the OS, the middleware, and we want more uniform hardware system architecture and firmware architecture across the board, where that in as many areas as that makes sense. The whole goal of that being greater compatibility and less engineering effort required. And as I had already talked about Project Cassini, SystemReady is the foundation technology that enables the cross-platform software ecosystem that we want to see. Now, if we look at, again, talking about how diverse the ecosystem is, one of the ways that we looked at it is we create a spectrum. And right in the middle there, you can see things that look very much like servers, of very standardized, we've high predictability on what the platforms do. We go over towards the right, we saw that the hyperscalers are wanting to do something different. And we realized that we need something that deals with them. And we've created a band of SystemReady that deals with the hyperscaler verticals. I won't talk about that. That's a totally other talk because there's plenty of material to talk about there. But let's go over and look on the right-hand side. Sorry, I'm getting my left and right. On the left-hand side, the vertical that we see there is more the edge node embedded IoT devices, where it is a very rich, very healthy ecosystem with lots of devices being produced every day. And what we're seeing over there is a lot of custom engineering, a lot of vertically integrated stacks, a lot of use of Yocto or Buildroot or OpenWRT, a lot of platforms based on U-Boot. And we want to preserve and want to keep that ecosystem vibrant and healthy. But at the same time, how can we bring in standards that help that ecosystem, while at the same time, if you look just a little bit further to the right, you can see all the OSs that we have listed there. And what that's trying to show is that for a lot of these embedded devices, as the software stack becomes more important, more complex, it's difficult to maintain. And there's an awful lot of value to be had by bringing in a third-party OS or Linux distro into the embedded platform, because then as a product vendor, you can rely on the platform, maintenance, security updates, and all of that an OS vendor would do without having to stand up a whole engineering team on your own to do it, right? So within that space, looking at that, the goal is take the ecosystem, support it as it is, don't require it to suddenly make a huge change, but at the same time, bring in the standards that make sense. And when those standards are adopted, enable new deployments that are easier to manage, less costly, more secure. Okay. So, as I said, again, looking at this, we can't just treat the whole ecosystem as the same. We recognize that there's multiple different parts of it, and that is the whole intent behind the structure of SystemReady. So SystemReady is one program. We have multiple bands. We have the SR band, which is ServerReady. It's exactly the same as the ServerReady program we already had. It's just the evolution of it. Next over is ES, which is embedded server. And realistically, the only difference between ES and SR is SR has much more stringent requirements on what how the hardware is built. What ES does, you can be considered ServerReady light, but it enables the use of the shrink-wrapped operating systems on devices that wouldn't be able to do full SR compliance. It's still UEFI, it's still device-free. And that's if you would care about that if those are the OSs that you wanted to run. Next over is IoT Ready, or IR, which is the one I'm talking about today, and that is firmly targeted at the embedded devices. And then finally, there's the Linux server band, which is targeted at the hyperscalers, which I don't really need to talk about today. Finally, there's two things at the bottom that are worth pointing out. The first one is with the little shield with the check mark, is the SystemReady security option. And this is an add-on certification that goes with any of these bands that says, if you have the security option, it means that you've correctly implemented secure boot and you have a hardware root of trust that goes right through and implements the features required for secure boot. And then finally, for our silicon partners, we have a pre-silicon program that provides testing and tooling to make sure system integrations are correct before you go to silicon. So if you are, for instance, integrating a PCIe controller into your silicon, you really want to take a look at pre-silicon and make sure that you're not running into common gotchas that impede hardware compliance in the future. Once again, the SystemReady, just like ServerReady, it's based on 3 pillars. We have our hardware architecture. Those first 2 columns talk about that. We have our firmware architecture, which is encoded in the SBBR specifications, and then we also have testing that goes along with it. So for those who are familiar with ServerReady, SystemReady looks very similar. And just to show that this is not something that's happening in isolation, we've already had quite a bit of engagement across all of our bands. In the SR and ES bands, we already have platforms that are certified. From Ampere and Gigabyte and SR, from Raspberry Pi and NXP, in the ES band. And then in the IR band, we have all kinds of interest. But given that IR is meaningfully different from the other two bands, we've got a large pipeline that we just haven't gotten any platforms out at the end of it yet. But you can be expecting announcements in the near future with some platforms becoming IR certified. Right, that was SystemReady. Let's talk about SystemReady IR specifically now. As I've already touched upon, the diversity, our very diverse embedded computing ecosystem does have some unique challenges to it, especially when you compare it to what we've done with, say, ServerReady. First of all, the software ecosystem is very diverse. You've got builds on Yocto, OpenWRT, Buildroot. You've got devices that are based on community distros, usually with a recompiled kernel or a custom kernel and boot path, and often a pre-canned root file system image rather than using the distro tools. We don't see a lot of shrink wrap OSs used. It's not that they're not there, it's just unlikely that they're being used in the devices because these are bespoke things that are crafted for specifically what they're going to do. The challenge here is we're asking these devices to do more and more. So we are asking them to do the regular embedded fixed function jobs, but at the same time, there's more and more talk about running cloud native workloads on them, Kubernetes, Docker. So how do we then manage to be able to support the ecosystem, the engineering ecosystem as it works, at the same time as enable these new workloads and make it possible? SoC support, very mature. I mean, you just have to look at the numbers of devices that are shipped with Linux. Linux is by far the preferred operating system on rich compute devices. However, this is all based on Linux's device tree ecosystem. Device tree grew up within the Linux ecosystem. It's not based on ACPI. It is different. It is. I don't want to get into the debate over device tree versus ACPI because that's not actually useful for this kind of conversation. But what we do know is device tree is adopted, well supported, preferred in a lot of cases. And so SystemReady, so we can't just ask for everyone to switch over to something new because it's not going to happen. Right. So we won't need to have a program that recognizes the realities of this particular market. Another thing is that the firmware stack that's often used is often U-boot. U-boot's the incumbent project, which is a very different history and set of interfaces from the EDK2 ecosystem, which is basically the reference implementation of UEFI. Again, U-boot, it is incumbent. It's well established. There's very few, it's very difficult to argue switching over to a new firmware stack without some real benefit that goes along with it. So we need a program that accounts for what is already there and how we can get adoption of this program without requiring a huge amount of engineering lift by the device vendors or the SoC vendors. So the whole design of IR is we want to choose standards that are appropriate, that make our engineering lives easier, but are appropriate for the embedded ecosystem and supports the way products are being made right now, so that we don't disrupt the supply chain of software. Right. How am I doing on time here? Okay, I need to hurry up a little bit. So the tagline remains the same. This enables just works for the ARM A-profile devices, but it works within the existing ecosystem. And what just works mean is slightly different with IR than what you would look with when you're trying to support a shrink-wrapped operating system market. So what IR means is it works with the existing technology and ecosystem. It's still we use trusted firmware, we use Opti, we use U-boot. It brings in UEFI as the standard implemented in U-Boot. It should be adoptable with minimal impact. And it enables a third-party OS deployments. Now, the experience on this one is not going to look exactly the same as what you see with SR and ES, where a release from 2 years ago is expected to work on the platform, because we know that these are bespoke devices. So for just works in embedded compute, we're starting with the underlying assumptions of, one, the firmware interfaces, we can very definitely standardize those, and those need to be standardized. But second, when it comes to device support of the silicon, the expectation is support. If you need additional support for the device in the kernel, that you get your drivers or your support, your power management support patches into the Linux kernel and supported with device tree so that the mainline kernel works. I'll come back to that in just a moment. Right, so here's just a comparison between the two. As I said, instead of string-wrapped OSs, the focus is more on the community and custom OSs, and the standards must work equally well for both using distros, pre-built distros, and for the custom Yocto and OpenWRT builds. Another interesting aspect just of the ecosystem, which I've touched on a bit, is that unlike SR and ES, where if you don't conform, if you aren't certified compliant with the specs in ES or SR, you don't have a product. If you can't land the OS that you care about on the product, you don't have a product. In the embedded ecosystem, the dynamics are very different, because there's little incentive, there's little direct incentive to conform with the specifications, right? You can still do the vertically integrated stacks, and if you're not quite standards compliant, you still can build a product. So in this space, the standards themselves have to show value in and of themselves and create pull in that way, rather than trying to do a top-down push of do it this way so that we're compatible, right? It's a bit more of a bottom-up approach, but it is it matches better with the embedded Linux community and how that whole engineering community works. Finally, the last thing is with IoT Ready, we still have a bunch of 32-bit parts, that it's not all gone to 64-bit. So with the IoT Ready band, we can do 32-bit ARM platforms. And we've got a lot more openness to doing waivers for non-compliance on those platforms. All right. Where am I here? One more note on the different banding. What you can see here, despite these being different bands, as much as possible, we're trying to use the same technology. And the arrows on this chart here show that if you've done everything for IR, you've actually implemented a lot of the same technologies that are in ES and SR. And so an ES platform provides all the same firmware interfaces and more as an IR platform. And so with the exception of device tree, because ES is providing ACPI instead of device tree, it all is the same stuff, right? So if you can deploy your platform on IR, you're going to be able to deploy your platform on ES and SR as well. And similarly, if you can deploy on ES, you can definitely deploy on SR, right? So there's a progression here that as you go further to the right, you've got stricter standards and greater conformance. But if you can land on something further to the left, then you're going to be able to land on the other bands as well. Current status of IR, the BSA, or Base System Architecture, and BBR documents are both released. They're available on the ARM website. EBBR, it's a community project being developed on GitHub. I'm the maintainer of that one. We're going to be doing a new release here in March. The latest copy of it, the release copy, since then we've added some greater specification on the UEFI specs. So go look at GitHub if you want to know what's going on. You can get involved with the bi-weekly meetings if you care about those kinds of standards. We have to get certified as in the IR band. There's basically two things we're asking. Number one, we're asking you to pass a set of tests through the ACS test suite that we'll be releasing. and then also to boot 2 unmodified Linux distros. Everything that's needed for implementing this already exists in the upstream projects. So if your product is based on mainline U-boot, if you're using TFA and Opti, all that you need is there. There's some configuration options that you turn on, but you can get up and running with the required UEFI interfaces very quickly. And we have some example platforms. CompuLab has a platform called IoT Gate IMX8, which we've been using as one of our major demonstrators. And we've got a full firmware stack for that implements it. The Rock Pro 64, which is an RK3399 platform, is also in excellent shape. We're doing some more work with that one. Most of the RK3399 platforms should actually be in really good shape. But if you're running latest U-boots, most of the interfaces that you need to turn on here really are in the firmware, and it's really software defined rather than the hardware. We will be producing some documentation that tells you how to do this stuff. Okay, last thing I've got is the elements of SystemReady IR, and I am low on time, so I'm going to page through these really quickly. You can go back and look at the slides or ask me questions after the fact. But this is the core bits. This is what must be there for SystemReady IR. First of all, its foundation is UEFI, the UEFI ABI. U-boot implements it. The EBBR specification defines how that works. The main value of this is instead of custom boot scripts or per platform weirdness that we need to deal with, it gives us a nice consistent interface so that the OS loader can make use of the firmware drivers up until the point of the OS is able to take over on its own. There's a little gotcha with this in that set variable is not required, whereas in regular UEFI it is required, which and there's some technical difficulties on that one, which is why it's not required yet, which may change some of how you deploy your OS to the platform. But other than that, it all matches. Second, device tree. The expectation is the platform must provide a device tree that can boot the mainline Linux kernel. It's the de facto standard, right? This is a very pragmatic decision of we have a rich ecosystem. This is what it is for IR, because that just slots right into the existing embedded Linux ecosystem. If the OS chooses to replace the device tree, it's fully capable of doing that. We can still do all the custom stacks, but the meaning of this requirement is that the distros, they can support a platform without having to go and do a bunch of shipping per board device tree files. Capsule update is required, and this is a new one that's been just added. If you're building a secure network device, in order to keep it secure and connected, you need to update the firmware. Capsule update is a common ABI that's already used by both Windows Update and the FWFD projects for delivering new updates to the devices. And so this is just a core part of how to build a device. Testing is the next part. We don't just define these interfaces. There are already tests out there. We're reusing the SCT and the firmware test suite as testing platforms, but we will be publishing an architectural compliance suite that integrates those things and basically gives you a USB key that you can test your platform with. And then finally, go look at Secure Boot. Right now with SystemReady IR, Secure Boot is not required. The security option is not necessary. But if you're building a secure connected device, you really want it. So if you're looking at SystemReady, if this sounds interesting, go and look at the security option as well, and go and look at the PSA certified program as well, because those are the Lego blocks or the building blocks that you will need to build a secure connected device that presents itself as a platform to third-party OSs. One more note on certification. We're spinning up the certification program now. More announcements will be coming out later in the year, but if this is interesting to you, just email us. There's the SystemReady contact email address at the bottom of the page. That will come to one of us, and we will get back to you to talk about your platform and what you want to do. And I have gone over by 7 minutes. I've got a slide here that tells you how to get started. There's no point in us talking about this now. You can look at it after the fact. And that is everything prepared that I have to say. So Berenice, I'll hand back to you.
Thank you, Grant. So everyone, I hope that was clear and you've understood a bit more about SystemReady. There's no questions in the chat box that I can see. Does anyone have a question they'd like to ask? It would probably help if you put your camera on actually, and I can see you wave or something.
Should be able to raise your hand or just pop in the chat as well. Well, Roy, this is the first time you've done one of these with just regular Zoom, and we're not sure exactly how well it's going to work.
Yeah. So I have a couple of questions to ask Grant that we've had from various people, and I'll ask this for the panel can join in as well. So just that you mentioned ES and IR bands, and I understand they're fairly similar. So what are the actual differences between them?
Okay, so the main difference between ES and IR is ES is targeted at if you are interested, if you care about the enterprise OS, enterprise Linux distros, or the other OSs that require a CPI, then ES is really what you want to look at, because it's exactly the same set of standards that are required for SR, but it's not as stringent, and it doesn't require quite the same things in the hardware, right? But you have to do a CPI. It is a larger lift to get your platform up and running because you have to work out how ACPI works. But once you've done it, you've got a larger selection of OSs to choose from. IR is targeted very specifically at the embedded Linux ecosystem, plus a little bit of embedded BSD or other OSs, but primarily this is at embedded Linux, which is firmly based on device tree at this moment, right? That's the working solution. So IR is targeted at that.
Okay, thank you. So John, perhaps I can come to you as someone who has products going through various bits of the SystemReady program. And perhaps you could talk a little bit about why you see it as valuable.
Yeah, certainly. Well, for us, simply because we don't just have one system. You know, we've been around for quite a while now, and we have various boards. We have ARM32, ARM64, and they go all the way up and down the scale from very small to very large. And every board, it becomes another set of documentation, another set of support docs, and then with every release, we have some customers who are saying, "Oh, well, you have Yocto and the other embedded ones, Buildroot, but I want to run Fedora on this, or I want to run Ubuntu on it." And for us, that's another support lift that we have to do until the mainline distributions pick things up. And so for us, what this does is this offloads. It distributes the support better. So if we have, like we were calling it, like ready to boot, where there's a firmware on the device, we ship it to a customer, they can choose the distribution or the software that they want to run on it, be it Yocto itself, or I could pass it over to Peter Robinson and Fedora can be installed on it and run, and give some of that support up as well. So really it spreads things out, and it also solidifies documentation, not just makes it simpler for us as a company, but it will intersect with the upstream distros. So Fedora's documentation will now be very similar to SolidRun's documentation and vice versa.
Thank you.
Peter, if you want to jump in on that.
Yeah, I mean, from a distro point of view, I don't want to have to produce a different image for every single device. I want to be able to say, you know, here is our known workstation image for ARM64, and it will just boot and run anywhere on any of the devices. And so, you know, from that perspective, you know, something like SystemReady gives standard interfaces, just similar to how you would see on like an x86 based PC, you know, you can put in a USB stick and boot any of the common distributions and it will just work. And so that's sort of bringing this to the ARM ecosystem. When I first started playing around with ARM things 12 odd years ago, it was like different kernel, different user space for just about every single device out there. And it was incredibly painful. And I've spent a lot of time within the Fedora Red Hat ecosystem making things just work. And we now support literally hundreds of ARM devices across the ecosystem with single images and single kernels, which makes, you know, the life for everyone a whole lot easier.
Olivier, do you have anything to add on that? You know, you see a whole variety of customers across our ecosystem.
Yeah, I think the message that Pete just gave us is exactly what we're trying to address here. Just making it easier for people to move across different products within a portfolio. So if a company has a dozen different products, just use one image and manage the devices the same way. Or if you're a software developer, just the ability to have one code base and be able to port that to multiple devices is really, really helping defragment the ecosystem. And this is what this program is all about. Removing friction.
Thank you. And I think one of the things you addressed later on in the talk, Grant, was the security option. And I'm assuming most people on here are, you know, already thinking about security. So that's quite a key part of things. So I don't know who this is best addressed at, but, you know, perhaps we should talk a little bit about what that security option gives you, and then what PSA certified, for example, would give you on top of that.
Yeah, so what the security option adds in is it says, if you're building a embedded, or if you're building a device where you want to delegate trust, say from the board vendor to the OS vendor, you need a scheme for doing that. So the security option brings in UEFI Secure Boot that already has all the thought process and thinking behind how to do that. So it's a standard that specifies this is what you will, these are the interfaces that you'll provide, and also that you will, you know, when you're doing firmware updates, that they are signed properly so that rogue firmware cannot be landed on the device. What PSA does, the PSA certifies, is it certifies that the thought process and the processes for how you create a secure platform have been adhered to, and it's so it works out how you create a secure platform, and so for right from hardware root of trust, all the pieces that need to be there to make the platform secure. So they're very much two pieces that need to go together if you're building a secure OS to land a third-party, or if you're building a platform to land a third-party OS onto.
Thank you. So they're two kind of parallel programs, but slightly related. Do any of the panel want to come in a bit on security there?
I mean, from a distro point of view, it's a similar story. You know, booting different devices and dealing with device security in different ways can only lead to confusion and compromise. Ultimately, if there's a standard way of doing something, it simplifies things. And generally, the best way with security is to keep it simple. And so similarly, you know, having standardized UEFI secure boot as a means of booting, having capsule updates for applying secure firmware updates. You know, it's known and tested. It's used across other areas of the IT infrastructure, and you know, people have the process in place for dealing with that. And so, you know, not having to reinvent the wheel is generally, for these sort of things, the better way to go.
Yeah, that's a really big deal for me, is that these are not trivial problems. These are hard engineering problems, and where we can make use of the thought process and the reasoning that goes behind it in other places, right? We've done this thinking in the client or the server space can we reuse that rather than reinventing the wheel every single time?